So this is the second part of the recitation that we are continuing with. So in this part, we are going to discuss twin paradox, which is not actually very paradoxical when we think about it, but we don't know some things yet to discuss it. So as we have said, the Alice is the twin that stays on Earth, and the Bob takes a fancy space shuttle to go to a trip to a planet that is 20 light years away as Alice measures it. Well, then this fancy space shuttle actually goes with the 0.8 c of speed to the direction of hell. So how much would you think that this guy's clock's affected? So let me quickly calculate the gamma factor over here. C. This is all squared, and then we have square roots. So this is going to affect him about, let's say, 0.8%. So this is our reversed gamma factor, obviously. So this one actually shows how much his clock is affected. But let's see. So who decides who goes at what rate? Like, no one. So if we take Alice to be stationary at the reference frame S and Bob to be moving in the reference frame with speed, this is S prime, then this all holds. So actually his clock has to tick slower and her clock is just at the regular rate. But if we think about it a little bit more, if we think that Bob actually sees himself stationary and actually sees Alice moving away at the other direction with some speed, then to Bob, the Alice's clock actually ticks slower, right? So shouldn't it be that if Alice agrees that Bob is not going to age as fast as her, then Bob has to say that Alice is not going to. Alice is going to actually age slower than him. So this is a little bit of a paradoxical part, because as we may know, nobody actually decides who goes with what speed, right? To Bob is perfectly stationary, and Alice is moving rather fast in the other direction that he doesn't want to be. So how to solve this thing? Now we have to discuss this little thing called length contraction, because in its form itself, without discussing the length contraction, it's a bit confusing to think about. So we are gonna have a little interlude about the length contraction. So we have seen that our observers at the inertial frames are the people who grade the space-time. So they are creating grids, right? So if we have this grids over here in a frame that actually moves with velocity, then our time grids actually become larger. But what happens to our space grids? So like if we go faster, our clocks get slower. But what about the rulers? Because quite frankly, there's nothing else in this world. There's like only time and there's length. So we can measure time, we can measure length, and we can measure mass too. But let's not discuss about the mass, because observers, actually we are going to see that observers also are the ones that are measuring the mass, and the mass is not mass also can get all the better, but that's not the problem. Now we are not measuring mass at all, so we are just measuring time and length. So we are measuring time differently in a moving inertial frame, but what about the length? Why not length? affected. It's affected. So, and this effect is given in your book with this formula, which is quite sweet and dandy. C square. So, as you may observe, this number is always smaller than 1. So it must be that the observed length in a moving frame is always going to be slower than the proper length. So if we measure some ruler's length in here as L0, this is the proper length. Here it has to go shorter here, which is great. So once we have established this, by the way, we can actually have this experiments, like this little Gedanken experiments in the session, the question session, if you wish. So we could just arrange a get together. Like we could just arrange a get together at the weekend and discuss all of that. We can actually make these experiments together at some point, but to keep the recitations rather short and sweet, I'm going to skip all of that. So what we say is that faster meant faster clocks tick slower. Also, faster means shorter. So if we go fast, our clocks will tick slower, and we are going to measure the length shorter, same length shorter. All right, so returning to the twin paradox is that we have Alice sitting here chilling, having coffee at good old Earth, and the Bob leaving all the comfort of his home and just going around with speed of 0.8 c to help. So here this planet is, as measured by Alice, is 20 light years away, which is pretty long distance, to be honest. And then this guy is not going to measure the same length though, really. No. So what we are going to have is this square root. So this is going to be 20 plus this number and 12 light years. So our length is measured in the Bob's frame of reference is 12 years, quite frankly. So to Bob just goes for 12 light years and then returns back for like 12 light years, right? So this is 24 light years of total voyage that has been done in speed of 0.8 c. So actually we are going to calculate how much time that Bob had spent in this space shuttle. To him, it is pretty straightforward. He goes back, he goes a distance of 12 light years in the speed 0.8 c for 15 years, and 15 years he comes back, and he had spent 30 years on that space shuttle, just clear as day. But what Alice thinks about it, Alice still stays at the good old Earth, and then to her, he goes away for 20 light years of distance in the speed of this. Then comes back, does the same thing and comes back. So she measures something like this. Years. So if they had started their trip with the age of 20, when they come back, Bob going after the trip, Bob is going to be 50 years older, 50 years old. And Alice is going to be 7 years old. Which I believe Alice would like to have this extra 20 years, but well, so what is the paradoxical situation actually solved by the length contraction? Because if it would be that we had measured time differently but length the same, then it would be a little bit confusing that if my clock ticks actually slower and then hers is faster, so I am going to think that her clock is ticking slower and mine ticks faster because the speed is all relative and whatnot. But what actually happens is that it's clear as the day that this asymmetry happens. So there's also an example in your books that you can check, which actually illustrates the Doppler effect in the twin paradox case, which I have given the Doppler effects for you to study. So I will, we may go back to Doppler effect after you have done your homework about the Doppler effect and discuss the example 1.4 in that manner. So we have completed the twin paradox example, but I also want you to think about something. This is called the barn and the ladder. So let's assume that you have a very large ladder of length L0 and you have a barn that you want to put this ladder in. Alright, so if the barn's length is also L0, that's perfect. Everything is perfect. You can just fit it right there no matter what speed that you're having, because you're just observing it from here. You hire somebody else to do it. They take the ladder, they put it into the barn and it fits like a glove. No problem. But then you decide that you are going to have this ladder and you're just grabbing it by the half. You're just carrying your huge ladder into the barn, same length apparently, but you go rather fast. So let's say you are again moving with the speed of 0.8 c because it's a nice number. And then what you're going to see is that this part of the ladder shortens, starts shrinking, right? Because you're moving and the ladder is moving, and it's like it is not the same length as before, because it was, if you grabbed it by this half, and it was the length of L0/2, and then once you have grabbed it and started moving, now you're actually measuring something pretty shorter, and you know that, you are aware of that. So what is going to happen is the barn, you are going to observe this barn actually not as stationary, because if you think that you're stationary and if you have this ladder and the ladder is all the same length, well, you're moving to the barn, or the barn might be moving towards you if you think about it, and the barn is shrinking in that sense because barn has some sort of speed. So think about this a little bit, and we may discuss it in the question session maybe later on. The barn and the ladder paradox, nice paradox, just Google it and you're going to find the answer right away. So I am going to continue with the electricity and magnetism and some relativistic momentum and such in the next video.